Did you ever wonder what makes gold conducting and sulfur not? And what about those semiconductors? What does it even mean that they're semi-conducting? I mean, they're at the basis of all modern electronics technology, which relies on electricity, so surely they must conduct a lot of electricity, or don't they? Well, the answer to all those questions lies within how atoms interact. As you know, in quantum physics, electrons can only have certain states within an atom, each described by a state function and an energy level. The atoms that are on the highest energy levels are also those that spend the most time in the outer layers of the atoms, so we call them outer shell electrons or valence electrons. They are the most weakly bound and are those that will be able to be shared with other atoms, forming chemical bonds. We call the states with lower energy the inner shells, and each state is in fact double, as it can contain two electrons with opposing spins. If we take two separate identical atoms far away from each other, well, it's clear that the electrons on each atom are described by the same states and the same energy level. However, if we bring those two atoms close together, to the point where the electron clouds overlap, we will have to treat them as a single quantum object. To lowest order, the states of the two atoms are then the superposition or the sum of the states of each individual atom. However, remember, quantum states have a phase, so there's in fact two ways you can add two state functions. You can add them in phase, in which case they just add up, and there's a non-zero probability of electrons being between the atoms, which will act like a bond between the atoms. Or you can add the two states out of phase, which is like having the left state minus the right state. And in that case, the probability of having electrons in between atoms will be reduced or even vanish. The in-phase superposition is called the binding state, and the out-of-phase superposition is called the anti-binding state. Clearly, those two superpositions are very different, so they also have different energy levels. The energy of the binding state is generally lower than of the anti-binding state, and both are quite different from the energy level of an individual atom. So when two atoms combine, the energy levels of each atom split in two, creating one lower energy binding state and one higher energy anti-binding state. The electrons will go into the lowest available state. In fact, something similar also happens to the inner shells. Their states combine, although much less so, and their energy shifts are much smaller. When combining two atoms, the energy level is split in two. When we combine three atoms, each level is split in three. And if we combine n atoms, each level is split in n. Some are binding, some are anti-binding, and so we get this collection of energy levels. If the number of atoms is very large, say 10 to the 23, the energy levels are so close together it hardly makes sense to distinguish them, so we then consider them a continuum of states and call them energy bands. The binding states of the valence electrons form what is called the valence band, very original. The anti-binding states form what is called the conduction band. Why will become obvious a bit later. The lower levels combine to what is inventively called the lower bands, which don't contribute all that much to the properties of matter, so we'll just ignore those from now on and concentrate on the valence and conduction bands. The valence and conduction bands are distinct, and so there is an energy gap between them, which we call the gap energy, or Eg. Now, what does all this have to do with electromagnetic properties of matter? Well, how full these bands are and the size of the energy gap will determine whether a substance is a metal, a dielectric, or a semiconductor. Let's start with insulators. These are materials in which the gap energy is of order 2 electron volt or higher, and each state in the valence band is occupied by an electron. The valence band is so full it can't take even one more electron up. The conduction band, however, is completely empty. How does it mean this is an insulator? Well, if it were a conductor, we'd have to have some electrons moving about. But consider an electron in the valence band at some position x. If we apply an electric field, will the electron move? Well, to move it needs to gain kinetic energy. But that would mean the electron would need to go into a higher energy state. Say it starts from this energy level here. It needs to go into the next level up, but that is already occupied, so it can't do that. Even the electrons in the highest energy state in the valence band would need to gain energy, but there is just no high energy state there until the conduction band. So unless you give the electron a higher energy than Eg, which is considerable, the electron is stuck in the valence band, and thus it's stuck where it is. It can't gain velocity, it can't move. So no conduction can occur. Think of it like one of those sliding puzzles, but there is no missing piece, so you can't slide the pieces, they're just stuck in place. In contrast, consider what would happen if the valence band were only half full. Electrons in the higher occupied levels can easily access other states with infinitesimally small energy increases. So even the slightest electric field will be able to give a tiny amount of kinetic energy to the electrons, so the electrons can easily move from one spot to the next. And the analogy of the sliding puzzle, it's like we removed half the pieces, so shifting the pieces is really easy now. And that is exactly the situation for a metal. What about semiconductors? Well, they are very much like insulators in that they have a full valence band and an empty conduction band. However, the energy gap between those bands is smaller, say of order 1 electron volt or less. A semiconductor at very low temperature is in fact a dielectric, since its valence band is full, conduction band is empty. However, if you increase the temperature, eventually some atoms will randomly have enough thermal agitation to kick an electron into the conduction band. That is, it will have a thermal energy exceeding the gap energy. And once it's in the conduction band, a small electric field can easily shift it to higher energy levels, so the conduction band electron will be free to roam, to gain kinetic energy, and that will lead to electric conduction. So that's why it's called the conduction band, even though the conduction band doesn't actually play a role in conducting electricity in metals, only in semiconductors. So how often does this happen that an electron goes from the valence band into the conduction band? Well, say the gap energy is 1 electron volt. At room temperature, kBt is 26 millielectron volts, so the Boltzmann factor is about 10 to the minus 17. So that means very, very, very few electrons. Perhaps 1 in 10 to the 17s will bridge that gap and jump into the conduction band. But in solids, there's of order 10 to the 24 atoms per cubic centimeter. So if you take 1 in 10 to the 17 of those, that still leaves 10 to the 7 electrons in each cubic centimeter. And that is enough to lead to a small but noticeable current. So clearly for such a semiconductor, at higher temperature, there'll be much more electrons in the conduction band and the conductivity will go up. When an electron jumps into the conduction band, something else is happening. It left an empty state behind. And that means that another electron in the valence band with a similar energy to the one that just left, when experiencing an electric field, will be able to use that vacancy to gain kinetic energy, so it'll be able to move. In the analogy of the sliding puzzle, the electron leaving means we remove the piece, so finally we can shift the pieces around. These vacancies are called holes, and you can think of them as bubbles in the sea of electrons. Consider a bubble in water in a gravitational field. The bubble is the absence of water. Gravity doesn't pull on the bubble, but it pulls on the water, which will then push the bubble up by buoyancy. So it's like the bubble is pushed the wrong way by gravity. In the electron gas, if there's a missing electron and you apply an electric field upward, the electrons will be pushed down, and so the hole in this electron gas will travel up. It's a bit like buoyancy again. So there's an upward force on the hole. That's an electrically neutral region of space being pushed in the direction of the electric field. Well, you can also see that as a superposition of a complete electron gas with no hole, so it's completely filled, and a positive charge in the middle of that. Electrically, these two are the same. The region over which the two overlap is neutral, like that vacancy, and a positive charge experiences a force along the electric field, like the bubble does. So really, this hole is behaving like a positive charge superposed on this full gas of electrons. This virtual positive charge is moving, so holes are moving charges, and they're also contributing to the current. So in semiconductors, we have two types of charge carriers, the free electrons in the conduction band, and the holes in the valence band. In pure semiconductors, also called intrinsic semiconductors, each hole is created by a free electron in the conduction band, and each electron in the valence band has left behind a hole, so the density of holes and electrons is the same. In both these densities, scale is the number of atoms times the Boltzmann factor, so the density of charge carrier depends exponentially on temperature. However, more often than not, the number density of holes and free electrons are not the same. This is the case as soon as there's impurity. Take a crystal of pure silicon, depicted here on the left with a blue nuclei and in black the electrons. Silicon is element 14, and in the table of elements it is surrounded by phosphorus and aluminium. Silicon has 4 valence electrons, and so in the crystal they are all shared between each other. Now replace one silicon atom with a phosphorus atom right next to it. The phosphorus atom has one more valence electron. It has 5 valence electrons. So if you replace the central atom here with a phosphorus electron, now suddenly you have one extra electron that doesn't quite fit in the valence band anymore. The valence band is full already, remember? So that electron is pushed up to the conduction band. And so now we have one electron in the conduction band where there was none before. So now we have one electron in the conduction band without having a hole in the valence band. That is called an N-type semiconductor, and they are very important in electronics. You could also replace a silicon atom with an aluminium atom. That's the element right next to it on the other side. It has only 3 valence electrons. So when you put it in the silicon lattice, there's one electron missing. There's one electron not enough to make all the bonds. So there's one electron missing in the valence band, so you have this hole in the valence band. That is called a p-type semiconductor. And in the p-type semiconductor, the dominant charge carrier are actually the holes in the valence band. They're equally important in electronics, and in fact, it's the juxtaposition of N and P-type semiconductors that makes electronics possible at all. So in doped semiconductors, the impurities can increase the density of electrons, that's called N-doping, or the density of holes, that's P-doping. Often, either holes or electrons are the dominant carrier. How that affects the conductivity and how they're used in electronic devices, that's a story for another time. That's all from me for now. Cheerio.